Okay, so thank you for having me, Michal. So my name is Segev Shlomov, and today I'm going to talk about robust non-Bayesian social learning. This is a joint work with Itai Arieli and Yakov Babichenko, which the latter is my advisor. Okay, so what we're going to see today, first I'm going to talk a little bit about informally our goal in social learning. Then I will present the model. We will see some related works, actually two. And then I will state my main result, which introduce the virtually additive dynamics. I will give one positive result, one negative result, then some the proof scheme very generally, because I find it very interesting, and some examples. Okay, so we're talking about social learning. And informally, our goal is to understand whether there exists a robust and non-Bayesian dynamic that's going to lead to learning in large networks. Okay? And in particular, when I say robust, I mean robustness with respect to the initial information of the agents. Okay, so the general model, we have three parts: a network, initial beliefs, and aggregation dynamics. So players are organized in a network. Think about Facebook. And we have a binary state space, 0 or 1. And at the first period, each player receives conditionally IID signals from the initial and form the initial belief. That is, let's say, given. Okay, I will talk about it in a minute. And then, after he or she forms the initial belief, at each period, their neighbors, each player see the beliefs of his neighbors, aggregate them into a new belief, report back, and so on. And so we denote by xtj of n the belief, let's say that the state of the word is 1, of player j at time t in network size n. And we're going to be interested in what happens to these beliefs, first as the time goes to infinity, and then as the network grows. Okay? Okay, so the first part is the network. So a network of n players is captured by n adjacency matrix T, and we denote by, so Tij over here equals 1. It means that player I observes player J, and that's it. And we don't assume any symmetry about this matrix whatsoever. So for a matrix T, we denote the influence vectors is just the normalized left eigenvector corresponding to the largest eigenvalue, but I want you to think about it as just the influence vector or the PageRank vector, which represent what is the influence of each player in the network. Okay? So the definition, Golub and Jackson defined a sequence of network to be influence vanishing if the influence of the most influential player approaches 0 as the network grows. And we're going to talk only about these kinds of networks, so we don't have some major player that control everybody else. Okay, the second part is the initial beliefs. So we denote by omega the set space of the nature, let's say 0 and 1, and we have some signal set S over here. So what is it information structure in social learning? So information structure is just a distribution over states and signals. Okay? So at the first day, player J gets some signal Sj, and he forms the initial belief, the probability, the state of the world is omega, given his signals. Okay, so this is what's happening in the first day. Okay. And on a binary state space, an information structure can be described as a distribution over 0 or 1. So from now on, when I'm saying information structure, just think about some distribution over the closed interval 0, 1. Okay, and I'm going to say it a lot, so I need you to get comfortable with this notation. Okay. So, and in addition, an information structure induces two ex post distribution. One given that the state of the word is 1, and the other given that the state of the word is 0. Okay? So this is the big picture. Information structure is a distribution over the closed interval 0, 1, and it induces one distribution over the closed interval 0, 1, given that the state of the word is 1, and one distribution given that the state of the word is 0. Okay. So, and the last part of the model is the dynamic. So xt, the belief of player at time t, is just a mapping from all of the available information up to time t to their current belief. And in the most general case, it can be depends on everything, on the initial information, on the history, on the aggregation function, on the way on the network, on the size of the network, and so on. And we say that a learning dynamic is information structure independent if the way people aggregate the information does not depend on the initial information. Okay? So this is the definition of information structure independent. So how we define learning? Yes, Inai?
So just to make sure, if I'm a player,
Yeah?
at a certain time, I send my neighbors my current belief. Not the things that I aggregated to form it, but just the belief.
So I will talk about it in a minute, but in each period, you just say what your belief at the current time, and the neighbors and your neighbors are able to see your belief, and they get the beliefs of their neighbors, and then they can aggregate it to the new belief. And then at the next period, they report the new belief and so on.
Report to the neighbors just the belief, not what they heard from me separately.
Of course, yeah. Okay. So given a network with size n, we define by x infinity as the time goes to infinity, the limiting beliefs of the player. And then how do we define learning? So we want that given that the state of the world is omega, the beliefs of the player will converge to omega as the network grows. So given that the state of the world is 0, I want the beliefs to converge to 0, and given that the state of the world is 1, I want the beliefs to converge to 1. Okay? And we're talking about convergence in probability, okay? Because it's random variables. Okay, question?
Shouldn't this be J greater than N?
What do you mean? No. I want, okay. So this is another important issue. I don't want that main aggregator can see what is going to be the state of the world. I want that each player will know the state of the world eventually. Okay, so this means that you can think about it as just the supremum norm. Okay, so everyone is going to be, if the state of the world is 0, then everyone is going to say 0. Okay? Yeah, J is a player. Okay, and N is the size of the network. Thanks. Okay, so just two most related works. So I think the basic dynamic is the Groot model. So the Groot suggested that player weighted average the neighbor's opinion, maybe the most, simplest dynamic that one can think about it. And Golub and Jackson in 2010 showed that if you have a real value state and with some zero mean noise, then you can use this simple dynamic to achieve learning. Okay. Then Levy and Razin introduced the Bayesian peer influence dynamic, and they suggest the following. If you have information structure, okay, with fixed prior, and you know the prior, for example, let's say the prior is 0.5, okay, then you can use a locally Bayesian updating, and you can achieve learning. So at each iteration, each player just apply Bayesian rule on the beliefs of his neighbors, and notice that it is locally and also Markovian because it only depends on time t. And then you can achieve learning for general state space. Okay. So our main results. So we are trying to establish a robust dynamic that is going to be good for a multiple, for a class of information structure. Okay, so we want one dynamic, one rule that people aggregate the information for a class, for a lot of information structure. So for example, if we take a class of information structure that's the prior is the same in each one of the class, then the BPI will be perfect. Okay? But this is just one example of class of information structure. So now think about, we have a class of information structure, a class of distribution over 0, 1, and also we have a class of distribution given that the state of the world is 1, and a class of distributions given that the state of the world is 0. Okay, so this is our scope. So what is it? A virtual dynamic. So a virtually dynamic with respect to some function f is defined by equation 4. And I want you to think for a moment about the function f as a function. Why we call it a virtually function? It takes some beliefs in 0, 1, and it converts it to a virtually belief in R. Okay, so you have some number, and which is the belief that the state of the world is 1, and you convert it to some number in R, okay, which is the virtually belief. So the family of dynamics that we suggest is the following. At each iteration, players get their neighbor's opinion. They apply the function f on them. So now from belief in 0, 1, they are going to be a belief in R, a virtually belief in R. And they just sum the virtually belief. Okay? Of course, later they apply f minus 1 to go back to a belief in 0, 1. So this is the virtually additive dynamic. And of course that these kinds of dynamics have desirable properties. For example, it only depends on time t plus 1, it only depends in time t, and you have some kind of anonymity. You don't care which one of the players gave you his belief, and you only sum the beliefs of your neighbors. So it's very simple in that manner. So questions so far about the dynamic? Very good. Okay, so the first result is a negative result. So Aureli et al. Introduced the following notation. So two information structure, P and Q. I remind you, information structure, think about just a distribution over 0, 1. Okay? So I say the two information structure, P and Q, overlap if P, given that the state of the world is 0, equals to Q, given that the state of the world is 1. Okay? And the trivial part of our result is that if you have two information structure, P and Q, and you have overlapping, then you cannot learn. Okay? So you can think about it the following way. You can't expect the beliefs of the player to converge both to 0 and to 1 in distribution if the distribution are the same. Okay? So you cannot achieve learning in not just in virtually additive dynamic, but in any dynamic. Okay? Any dynamic, you cannot achieve learning. So this is the negative result, and it is very negative. Okay. Okay, so what is the positive result? So just a quick reminder about what is learning. So we say that a class P is learnable if you can learn each one of the information structure in your class. And our main theorem states the following. So if you have a class that is compact and convex, then it is learnable if and only if P does not contain overlapping information structure, which means that no overlapping is sufficient and necessary condition for learning to happen. Okay? So in fact, the result, you can think about it that the one obvious obstacle, so of course, if you have overlapping information structure, you cannot learn, it's very trivial and obvious. So the one obvious obstacle to learning is in fact the only obstacle, and even a simple class of virtually additive dynamics can learn robustly. Okay, so this is our main result. Questions? Nice. So just one slide about the proof. Some of you may find it interesting. So given a network with size n, we can write the virtually belief as our matrix time t minus 1 dot the initial beliefs of the initial virtually beliefs of the player. Then we use the Rubinius theorem to state that if some weighted average of the initial belief, so I remind you that Vj is just the influence of player j, so some weighted average of the initial belief is positive, then the belief will converge to 1, and if it is negative, it will converge to 0. Okay? So this we get from the Rubinius theorem. Then we used some generalization of the weak law of large number to show that this weighted average will converge to the expectation of the function f. And so now we only need to show that the expectation is positive if the state of the world is 1, and negative if the state of the world is 0. So we show that if our class P is compact and convex, also the class of the two induced distribution are compact and convex. And so if we have two compact convex classes, we can, and they are not containing overlapping, then we can separate them with the Hahn-Banach separation theorem, and then we can achieve the learning. We only need to show that if there exists a function, there is also a surjective function in order to our dynamic to be well defined, but we show it at the end. Okay, so this is the main idea of our theorem. And as a corollary of our result, then if you have some function f that can separate the two sets, then if all the players will use this function f, you will get learning eventually. Okay, so this is another corollary. Okay, some examples. So the first basic example is the class of information structure where you have the support is size 3, 0.2, 0.5, 0.8, and with some probabilities. And here in A, you can see that P1 and P0 can be separate. You don't have overlapping here, so you can separate it and you can achieve learning. And here you have overlapping information structure, so you cannot achieve learning. Okay. Another useful example is unbounded information structures. So we say that an information structure is unbounded if 1 and 0 is in the support, okay, if you have a positive probability to get them. And usually in Bayesian social learning, if you have the property of unboundedness, then you can achieve almost everything, okay? But in this setting, we ask if you can use a simple dynamic that is going to lead to learning and not a complicated Bayesian dynamic. Okay, so the question is whether there exists a simple question. Okay. So the answer is no, okay? Just some example for information structure P and Q, okay? If you take them, then they are overlapping, okay, and both of them are unbounded. So you cannot achieve learning even if you have the unboundedness property. Okay. And maybe the last example is what happened to a fixed prior. So we already saw if you have a fixed prior information structure, then you can use the BPI dynamic to learn. But we also show in our paper that you can use also the log likelihood dynamic, and then you can achieve learning. So, and we also show that the log likelihood is actually identical to the BPI. Okay, so we provide an alternative proof for the BPI. But think about the class where you know that the prior is half, but very close to half. Okay? So this class is not learnable because you have an overlapping information structure, and so you cannot use the BPI, and actually you cannot use any dynamic to learn. But for example, if you know that the prior is very close to half and you have some assumption about the variance or the information that a player have, then in this case you can learn with the virtually additive. Okay, so you cannot learn with the BPI, but you can learn with the virtually additive dynamic. Okay, and just to get some notation of what so what are the functions look like? So think about now the fixed prior class. Okay, so when you know that each one of the information structure has expectation of half, then which kind of virtually additive dynamics are going to lead to learning? So basically, any function with here under the blue and below the red is going to lead to learning. And you already saw that the log likelihood function, this is the black one, is just one among many other virtually additive functions that is going to lead to learning. Okay, so just to conclude, I want to leave time for some questions. So we saw what is social learning, just discuss it a little bit, and we saw the notation of overlapping information structure. We saw that if you have similar initial distribution in the two states, then you have, this is the definition of overlapping information structure. And our main results state that if you have no overlapping, then you can learn with simple and Markovian dynamic. And if you have overlapping, then you cannot learn even with some complicated aggregation function. Okay, and I think that it's. Okay, question.
Questions? Questions? Yes?
I guess I have again a high-level question about the work in the literature. So can you hope for finite state of convergence?
Can you speak louder, please?
Can you hope for finite states of convergence? You talk about learning in the linear, but how about finite states?
Okay, so this is a good question.
Repeat it.
Okay, yeah. Sure. So the question was, can I say something about the rate of convergence of the learning? Okay, so I think. Okay. So in the virtually additive dynamic, the rate of convergence is very, okay, I think is very fast. Why? Because, okay, if I go to the proof itself, then convergence here, okay, convergence is very fast because this is just like convergence of Markov chain, of the distribution of a Markov chain, okay, the limit distribution of a Markov. This is, I think, very fast. And the one obstacle that will maybe affect more about the rate of convergence is here, when we use the weak law of large number. Here it depends on the information structure. If the information structure has a large variance, then it might take a lot of time to converge here. Okay, so this is the main bottleneck of the rate of convergence. And of course, you can. There is a lot of work to do here. Maybe we can bound it, and maybe you can show something that will be faster. Maybe this is going to be. This is for the next paper, for next TC. Okay. Other questions? Thank you.